Morning, everyone. Just continuing here in our probability distribution unit. Kind of going to take a little bit of a 2-day, I don't want to call it a lapse, but we're just going to move slightly in a different direction for the next 2 days. My algebra lovers, my students that love algebra, you're going to love the next 2 days, okay? Because they're very kind of mathy, they're no word problems, it's just straight algebra, you're going to love it. And my non-algebra students, I hope you just feel, hey, this is pretty cool, and you enjoy it, okay? It definitely will be included on your test. So don't feel just because we're kind of moving in a slightly different direction that you're thinking, geez, this, I don't have to worry about it. It will definitely be on your test. Okay. Binomial theorem part 1 today. Binomial theorem part 2 tomorrow. Okay. Let's take a look at our series examples. Well, when I look at each of these examples, let's just highlight. What I'm looking at is a binomial raised to an exponent. That's why it's called binomial expansion. A binomial raised to an exponent, a binomial raised to an exponent, binomial raised to an exponent, binomial raised to an exponent. And way back in grade 10, we learned about algebraically expanding things. So let's start right off at the beginning. We know that anything with an exponent of 0, whether it be a whole number, whether it be a variable base, anything raised to the exponent 0 is 1. So that's easy. We also know that anything raised to the exponent 1 is actually itself. So 5 to the exponent 1 is 5. A to the exponent 1 is A. A plus B to the exponent 1 is A plus B. Okay, so far so good. Now, when we look at our next example, you're familiar back from grade 9 that if I'm squaring that binomial, it's best for me to write it out. And then I am going to use the beautiful process of FOIL to expand it. First times first, outside times outside, inside times inside, last times last. And when you expand things, we collect like terms, and it's cleaned up beautifully. Okay, take a look at the next one. So now I'm not squaring the binomial, I'm actually cubing it. And when I teach this in grade 9 and grade 10, I ask my students to keep their first binomial out in front, and then I ask them to FOIL the next two. So I'm going to keep the first binomial right out in front, and I'm going to FOIL the next two, first times first, outside times outside, inside times inside, last times last. Now, I can do a little bit of cleanup of the second bracket. And I'm not done. I've got to expand. I've got a binomial multiplied by a trinomial. So that expansion is going to be what I call party analogy. A is going to go in and expand to each of the terms. And then B is going to go in and expand to each of the terms. So let's bring A in. A times A squared. A times 2AB. A times B squared. Now I'm going to bring B in. A squared B. 2AB squared. And B cubed. And I'm going to look to collect any like terms. I see some A squared B's. And I see some A B squareds. So I'm going to clean it up. A cubed plus 3A squared B plus 3AB squared plus B cubed. Now, before I go on to the next one, because you can already sort of see what's happening here, I just want to take a little look at something. Exponent 0, the result was one term. Exponent 1, the result was two terms. Exponent 2, the result, three terms. Exponent 3, the result, four terms. So I think it's pretty fair for me to ask you, exponent 4, my final line have? And I think everybody out there will agree with me and say 5 terms. We're just developing some strategy, okay guys? So just keep it in your mind. Okay, this one's going to be it's a plus b times a plus b times a plus b times a plus b. What I'm going to do with this one is I'm going to FOIL the first two binomials and FOIL the second two binomials. Now, I've already FOILed that, and I already know that it's a squared plus 2ab plus b squared. So I think I'm pretty safe in writing that down. Now, what I've got going on here is what I call another party analogy. A squared's got to go in and speak to all of these people in this party. 2ab has to speak to all of them. B squared has to speak to all of them. So let's go slow. Hopefully I don't make a silly here. A squared times a squared. A squared times 2ab. A squared times b squared. 2ab times a squared. 2ab times 2ab. 2ab times b squared. Let me just get that out of there. I'm going to need some more space. A squared plus b squared. B squared times 2ab. B squared times b squared. Okay, let's see. I'm going to use my color and do my matchy-matchy. I've got some a cubed b's. I've got some a squareds, b squareds. And I've got some a b cubes that need to be collected. Okay, so a to the 4 plus 4a cubed b plus, sorry, my mistake, 6 a squared b squared plus 4ab cubed plus b to the 4. Now, can I just show you something in terms of, you might have been wondering, Miss Martel, how did you know to write the terms in that order? How did you know, like, does that order particularly matter? Yeah, it kind of does. Let me point something out. A to the 4, a to the 3, a squared, a, no a. Watch how cool this is. No b, b to the 1, b squared, b cubed, b4. That's not just happening on an off chance. Okay? So again, just verifying the exponent was 4. 1, 2, 3, 4, 5. 5 terms. So we're developing theories here in doing this without even really know we're developing theories. Now, what have we discovered? Well, if I gave you the next question, a plus b to the exponent 5, you can very logically see that this is time consuming and we need to start looking if there's any patterns. The first pattern we've already pointed out. I want you to look at my A term in all of your answers. What do you notice about that A term? The powers are descending. 4, 3, 2, 1, A to the 0. 3, 2, 1, A to the 0. 2, 1, A to the 0. Now, in that same reference, put your eyes on the B's. Put your eyes on the B's. And what do you notice about the B's? The B's are not descending, they're ascending powers. So without really knowing, I'm developing a series of rules here by just looking at patterns. Exponent, number of terms. Exponent, number of terms. Exponent, number of terms. So the first rule I'm developing is, hey, whatever my exponent is, I'm going to have one more term in the final answer. That's rule number 1. Rule number 2, whatever my first term is in the binomial that I'm expanding, those powers better be in descending order. Hey, rule 3, whatever my second term is in that binomial that I'm expanding, those powers are going to be in ascending order. Totally cool. Okay, when you're ready, let's flip. Notice we're doing the example that I'm sure you completely expected, but notice I've given you basically no room. And the reason I'm giving you no room is because we don't really need it. Okay, let me show you. The exponent is a 5, so that is telling me that I'm going to have 1, 2, 3, 4, 5, 6 terms in my answer. I've already developed that. Okay. The first term is an A. Those powers seem to go in a descending order. So I feel comfortable writing that in because I noticed that pattern on the first overhead. The second term, the powers seemed to go in an ascending order. So I also feel very, very comfortable with what I just wrote in. What I'm kind of sketchy on, okay, and what I'm kind of feeling uncertain about is I'm not sure where those coefficients, where they came from. Hold on for a brief moment, okay? 1, 4, 6, 4, 1. 1, 3, 3, 1. 1, 2, 1. 1, 1. I'm feeling iffy. I don't have a clue where those are coming from. Well, guess what? That's what I'm going to show you, and it's quite cool. It's not as easy to spot the pattern in the numerical coefficients. That's what we just talked about. But I want to show you something that they call Pascal's triangle. Okay? Pascal's triangle, let's take a look. It starts at 1. Each on the diagonal is a 1. And if you take a look at the pattern, what you see is this beautiful pattern. 1 plus 2 is 3. 2 plus 1 is 3. Each row always starts at a 1. and ends in a 1. But as the pattern develops, the middle numbers are derived from adding in the previous row. So each row starts and ends at 1. Okay, now hold on. Let me keep an eye on this, and then let me go back to our examples. 1 1, 1 2 1, 1 3 3 1, 1 4 6 4 1. Isn't that cool? That's where these coefficients are coming from. So the exponent is like the row. This is row 0 with 1 term. Exponent 1, or row 1, this is 2 terms. Exponent of a 2 had 3 terms. Exponent of a 3 had 4 terms. Exponent of a 4 had 5 terms. So if we wanted to keep this pattern going, exponent of a 5 would have 6 terms. We'll build it in a second. Exponent of a 6 would have 7 terms. Exponent of a 7 would have 8 terms. Let's see if we can build it together. Starts with a 1 and ends with a 1. Middle numbers are going to be 5, 10, 10, 5. That's anything with an exponent of 5. Starts with a 1, ends with a 1. Middle numbers are going to be 6, 15, 20, 15, 6, and 1. So anything with an exponent of 6 is going to have 1, 2, 3, 4, 5, 6, 7 terms. Anything with an exponent of 8 starts with a 1, ends with a 1. Anything with an exponent of 7 is going to have 1, 2, 3, 4, 5, 6, 7, 8. So what we've just discovered is the exponent tells us how many terms, 1 more. Okay, so exponent of 5, 6 terms. First term uses descending powers. Second term uses ascending powers. And your coefficient that goes out in front of each term comes from Pascal's triangle. So 1, 5, 10, 10, 5, and 1. No brackets, no foiling, no worrying, none of that good stuff. Let's clean this up just one more time. B to the 0 is 1. 5a4b, 10a cubed b squared, 10a squared b cubed, 5a b to the 4, and a to the 0 is 1, so our last term is just going to be b to the 5. Is that not the neatest thing? It really and truthfully is. So some of you are thinking, geez, Miss Martel, like what if you gave us an exponent of 15? would we, in order to know the lead coefficients, have to draw Pascals? No. As of today, yes. Okay, as of today, you're going to have to be able to draw Pascals and know the pattern of Pascals. As of tomorrow, I'm going to teach you a new trick. Okay, so don't fret about it. We're just going to practice today and whatnot. Each row starts and ends with a 1. Okay, let's take a look at doing an example together. First thing that I look at, how many terms am I going to have? This is telling me that I'm going to have 7 terms. 1, 2, 3, 4, 5, 6, 7. And I'm going to put pluses in between. Okay? I like to leave a little bit of, a little bit of room because I write big. Second thing that I do after I draw out how many terms, I start working with my first term. A to the 6, A to the 5, descending, right? A4, A3, A2, A to the 1, A to the 0. I work with the second term. Ascending, B0, B1, B2, B3, B4, B5, B6. Now I have to take a little bit of time, right? So if I know that I'm dealing with exponent 6, that's row 6, 7 terms. So the coefficients that I'm going to deal with are 1, 6, 15, 20, 15, 6, and 1. And the only final thing that I do is just kind of clean up. A to the 6, 6a5b, 15a4b squared, 20a cubed b cubed, 15a squared b4, 6ab5, a to the 6. Is that the neatest thing? I love it. I love this lesson. Okay, with anything in math, we've got to make it harder. That's just the way things work. So we're going to get into examples that are a little bit harder now. So always start with the exponent. The exponent is a 4, so that means that I'm going to have 5 terms. Okay, start with your first term. Your first term always is in descending order. Now, why I'm slowing down on this particular example is we have never seen anything in a question so far that's been a negative. Everything that we have done has had plus b, plus. So my second term is the entire yellow highlight. It's negative 2y to the 0, negative 2y to the 1, negative 2y squared, negative 2y cubed, negative 2y to the 4. You got to be really, really, really careful. That's why I'm pointing that out. Let me highlight that so that stands out in your note. Now, the Pascal triangle part isn't really a big deal. Exponent of 4, 5 terms. I'm going to have a 1, a 4, a 6, a 4, and a 1. Why? Because I've got that memorized. I've got that picture memorized. Okay, now the part that sometimes gets you guys is the cleaning up. So I like to take this slow. 1 times x to the 4 is x to the 4. Negative 2y to the 0 is just 1. So that's super easy. Okay, now let's work with the coefficients here. Negative 2y to the 1 is negative 2y to the 1. Negative 2y times 4, negative 8, x cubed, y 1. Negative 2y squared means negative 2 squared. Negative 2 squared is 4. 4 times 6 is 24. X squared, y squared. Negative 2y cubed. Negative 2 cubed is negative 8. Negative 8 times 4 is negative 32. X to the 1, y cubed. 1 is 1. X to the 0 is 1. Negative 2 to the exponent 4. 16. Y to the exponent 4. That's where you guys have to take it slow, because most of your silly mistakes will occur in your signage, okay, and with your exponents. But we got a whole bunch more examples, so when you're ready, we'll flip and we'll move into, you know, definitely more challenging examples. Okay, let's give her a shot. Okay, so first thing that I see, exponent of 5. Exponent of 5 tells me 1, 2, 3, 4, 5, 6. I'm going to put my pluses. Okay. Now, my first term is 2a, the whole entity. So that's going to be 2a to the 5, 2a to the 4, 2a to the 3, 2a to the 2, 2a to the 1, 2a to the 0. My second term, let me highlight it in orange, is negative 3b. So negative 3b to the 0, negative 3b to the 1, negative 3b squared, negative 3b cubed, negative 3b to the 4, negative 3b to the 5. So my first term has been dealt with in an ascending power. My second term has been dealt with in an ascending power. I'm dealing with my fifth row, which means 6 terms. So my coefficients are going to be 1, 5, 10, 10, 5, and 1. Okay, so you're going to get some marks for that. Okay, you are. But the simplification step in this particular lesson is really important. So let's go through here. Anything to the exponent 0 is just 0. 2a to the 5, that means 2 to the exponent 5, a to the exponent 5. Okay, you might need your calculator for the next one. Let's take a look at what I'm looking at here. 2a to the 4, that means 2 to the 4. 2 to the 4 is 16 times 5 times negative 3. Negative 240, a to the 4, b to the 1. Slowly but surely. 2a cubed, that means 2 cubed. 2 cubed is 8 times 10. Now hold on, negative 3b squared. So negative 3 squared is times 9. 720 a cubed b squared. Let's go slow. 2 squared is 4 times 10 is 40. Negative 3 cubed. Negative 3 cubed is negative 27 times the 4 times the 10. Negative 1080 a squared b cubed. Okay. Negative 3 to the 4. Negative 3 to the 4 is 81. 81 times 2 times 5. 810 a b4. 2a to the 0 is 1. 1. Negative 3 to the 5. Negative 3 to the exponent 5 is negative 243 b5. So where my students end up usually having some issue is in this simplification. Okay, you got to go real slow, and you do the coefficient first, then the letters. Coefficient first, then the letters. Okay, they need some, they're going to take some practice. Okay, let's look at the last two examples. Now, the last two examples, obviously, look harder. Yeah, they are. Now, why are they harder? Because of that guy right there. And if you think back to grade 11, okay, if you think back to grade 11, 1 over x can also be written as x to the negative 1. So I'm going to change this question, and I'm going to change it to 1 minus x to the negative 1 all cubed. I don't want to have fractions. I just want to have base and exponent. I just want to have powers. Okay, so let's go through. Regardless whether the question is hard or easy, the process is identical. Exponent of 3, 1, 2, 3. Four terms. First term is a numeric term. 1 to the 3, 1 to the 2, 1 to the 1, 1 to the 0. The second term is this ugliness with the negative. Negative x to the negative 1 to the 0, negative x to the negative 1 to the 1, negative x to the negative 1 squared, negative x to the negative 1 cubed. Now, lead coefficient. Row 3, 4 terms, 1, 3, 3, 1. Okay, so I usually don't have students having problems with this line. It's the cleanup. So let me again verbally lead you through. Anything to the exponent 0, I don't care how ugly it is 1. 1 cubed is 1 times 1. That's easy. Okay? Now, let's start with this little hot mess here. I actually might put in an additional line. 1 squared is 1. Now, negative 1, don't forget, there's a negative 1 there. Negative 1 to the 1 is negative 1 x to the negative 1. Notice you multiply those. We'll clean it up in a sec. 3, 1 to the 1. Negative 1 squared. Negative 1 squared is 1. X to the negative 2. 1 is 1. 1 to the 0 is 1. Negative 1 cubed is negative 1. X to the negative 3. You have to remember that in front of this, there's a 1. There's a negative 1 in front there. Okay, So 3 times 1 times negative 1, x to the negative 1. 3 times 1 times 1, x to the negative 2. 1 times negative 1. Now, you cannot leave things with negative exponents. So there is one more line here. Bring them down. Bring them down. Bring them down. And don't worry about getting a common denominator. You can leave your answer exactly like that. These take practice, guys. They really do. I'm not gonna lie to you. Okay. Let's rewrite our last example as x squared minus x to the negative 1 to the 4. That's what I want to use. And I know that I'm going to have 1, 2, 3, 4, 5 terms. Okay. First term is x squared to the 4. X squared to the 3. X squared squared. X squared to the 1. X squared to the 0. That part's easy. Second term is negative x to the negative 1 to the 0, negative x to the negative 1 to the 1, negative x to the negative 1 to the negative or to the 2, negative x to the negative 1 to the 3, negative x to the negative 1 to the 4. Lead coefficient. Exponent was a 4, row 4, 5 terms, 1, 4, 6, 4, 1. Again, this is not going to be the step. It's a very memorized step. You can easily gravitate to it. It's the next part that's going to take some time. So let's go through baby steps. 1 is 1. X squared to the exponent 4, multiply them. X to the 8. Anything to the 0 is 1. That wasn't too painful. 4. X squared cubed, multiply them. Negative 1 to the 1 is negative 1. X to the negative 1. Not too bad. 6. X squared squared, multiply them. Negative 1 squared is 1, x to the negative 1 times 2. Not bad. 4. X squared to the 1 is x squared. Negative 1 cubed is negative 1, x to the negative 3. Keep going. 1 is 1. X squared to the 0 is 1. Negative 1 to the 4 is negative 1, x to the negative 4. Okay. X to the 8. 4 times negative 1 is negative 4x to the... Now careful here. When I'm multiplying powers with the same base, I add the exponent. So 6 plus negative 1. 6 times 1 is 6. When I'm multiplying powers with the same base, I add the exponents. 4 plus a negative 2. 4 times negative 1. When I'm multiplying powers with the same base, I add the exponents. 2 times negative 3. X to the negative 4. So the only thing that's wrong in my answer right now is it's in BF because I am not allowed to leave negative exponents, and I definitely won't. Okay, I know this note is quite a little bit of writing and little letters and exponents and whatnot. I'll definitely attach the PDF of my filled in note. And definitely there's not a lot of homework, but definitely give the homework a shot. You have to be able to do these types of questions. This is what you're going to be tested on. Okay? All right. Hope this was helpful. Take care. See you guys tomorrow.